Welcome back to This One Time. And here we are, part two of the live engineering strike force with Gabby. So a quick recap. This one time, we like to talk about our journeys in hardware engineering. You always hear that hardware is hard, but never really get to hear why. So we're here to talk about the why and get into the nitty-gritty details of what makes all of this so fun. So hopefully folks out there can learn some lessons and help get to their goals and achieve their missions that much faster. So this is the first time we have this format. Last episode, which 2 weeks ago, we decided to do something new, which is talk about an engineering challenge that we were working on in real time as it was evolving. And the engineering challenge that we're talking about was integrating a sensor to measure the opening and closing of the jaws in our nail picking robot. And we set up the problem last time, talked about why it was important. If you want to get the backstory on that, you can go back and listen to the last episode. And in the intervening 2 weeks, Gabby dove right in and got to work on this. And I'm not going to spend too much more time setting it up. I think we can just kind of dive in to the details. Jory, do you want to ask any other like setup or questions before we dive into it?
Well, I do want to just, say how it this whole collaboration, I mean, this is exactly why we started the show in the first place. And we got an awesome email from Joe, what's his last name? Mm,
Cavaletto?
Cavaletto, thank you.
Yeah.
Um, and giving us all kinds of detail, or giving the engineers all kinds of detail about his ideas, and that's exactly what we were hoping for. So that's really exciting. So thank you, Joe.
Yeah,
um,
thanks, Joe. If you're out there and you're listening to this one, really was excited when that email came through, and it was awesome, awesome work in there. And we might even talk about it a little bit during the episode here.
for sure.
Yeah, yeah.
And yeah, Gabby, how do you feel about the 2 week challenge? Do we need some victory music?
Yeah, I think having a real time limit, a public time limit like that was good because instead of like pushing off the project to later when things are less busy, which never really happens, just got it done. So that was exciting. It feels good, and it's done, and the parts are going to be fully in tomorrow to get it tested. So it was like actually accomplished in
Yeah,
the time frame.
So
yeah,
I think maybe we're gonna need part three to see in 2 weeks.
Does it work?
yeah, yeah. I think
Or
we should definitely do it.
Yeah.
We can do a part three.
Hopefully
In
happy
robot. Yeah,
version.
yeah. I'll also add that this is definitely not the only thing you're working on the last 2 weeks. Like, there's a lot of other stuff that we've been working towards this next deployment on. So this is like part of a lot of work that happened over the last two
right.
weeks. Just so
Yeah, I
yeah,
think that Gabby made that clear in saying that this was this was just one little piece,
yeah,
right?
yeah,
It was a fun one. Yeah.
But
yeah.
good. I'm so glad. So tell me about your experience. I'm sorry about my lighting. It is super gray here today, and I'm trying my best to give an actual light, but I can see it's not doing much good. Okay, go.
Yeah. So our process was first under in the last episode understanding what the problem was, and we realized that our main pain points on the last one and going forward are that we're in a really dirty, dusty, and kind of violent environment. So that's like the number one requirement is to protect against that.
For sure.
Um, and then generally the engineering process is figure out what are your requirements, then brainstorm your solutions, and then go about designing. When you go in with like an idea already in mind, then sometimes you can be closed-minded about things. So yeah, I guess I can screen share
Yeah.
now.
We have a few slides that Gabby made here. We'll share.
Very excited to see.
So these are actual design review slides that we reviewed with the team, basically deciding what are the requirements. And what's shown on the right kind of jumps a little bit ahead to a solution because it was when we had a solution. But really, when forming requirements, you're not thinking about the solution at all. So, um, and it kind of like a solution might just fall out of it or it may not. So we needed to know how open, not just if it is open or closed. So we needed resolution and accuracy of whatever sensor is being used. And then we needed to be able to measure the full range of all the way open to all the way closed, and also account for if the ends of the jaws wear a little bit, they might go in basically like this. And we needed to be compatible with our basically our existing system, just plug in. So 24-volt sensor input, and then 0 to 10-volt output. And also didn't want to spend an exorbitant amount of money, but something about prototyping is that it does just cost more when you're prototyping. So as long as it's not precluding a cheaper solution when you're mass producing, then it's sometimes worth it to just spend a little bit more now to get what you need. Yeah. So all of this is eventually getting towards the picture on the right. But in brainstorming, the most obvious solution was still use a potentiometer that mounts between those two blue circles, and which is where we had it originally, but just get something a little more robust and guard it better so that we're using kind of a proven technology, a known solution, and can kind of just drop it in.
Well, it didn't work originally.
It didn't work originally, but the concept isn't necessarily a bad one. Like, the reason it didn't work before was it was not a super robust sensor. It wasn't meant to be used in a really difficult environment. Right. And we also didn't have anything around it to protect it. From a mechanical perspective. From an electronic perspective, we knew that whatever we were going to use had to be this input and output that we have here, because the whole mismatch components we had before really just wasn't working.
Yeah, so we wanted to stay in that industrial automation paradigm, and like 24-volt DC is by far and wide the most adopted control level, and 0 to 10-volt DC as an analog input or output is also the standard for industrial automation. So we wanted to stay within that paradigm as much as possible.
Which is good, because sensors that are available for industrial use are going to be a little more robust than something you get on like SparkFun, and they're also all pretty much meant to be used with industrial automation standards. So that's a good thing. So yeah, the original just potentiometer thing, it could work, but there are some major drawbacks, which were moving parts that come in contact with each other. So that's going to be a wear item. It's still pretty close to where the nails are picking. So if your guards fail or something manages to get around the guards, that's a risk. And having dust come in there, that's another thing that's going to reduce your lifetime. So something that wasn't a requirement, but something that would have been really nice, is to have a solution that has no moving parts and is non-contact. So that's kind of what led us to where we were here. And another requirement that isn't stated on the screen, but we were operating in, was not to require any major changes to the parts that are already here, which is everything shown here. Because 3 out of the 4 of these jaws are already built, so we'd have to like order new parts, swap out all the parts. That would have a lot of associated time and cost, both from a parts perspective and also from we have a lot of things to put together and only so many people.
Yeah, and blocking the software team is now getting into using the actual hardware for their development. So anything we do at the robot now is blocking the software team.
Yeah, makes sense. You got to work together. And this whole thing was, Alex wanted it, so you got to make the software guys happy.
Exactly. So, looking at, I guess we can look here still, at non-contact solutions, the parts that are moving are the jaw. The way it works is there's a piston, and a pneumatic piston here that is moving up and down, and that brings this clevis up and down and moves these jaws in and out, kind of like salad tongs. So, the motion is here, the motion is here, But part of the motion that we haven't really been paying attention to until now is this moving vertically is something that we could be measuring to get a proxy for the motion down here. So this area was appealing because it is much further up and there's a big plate in between, so it would be inherently more protected. So that was where I was looking to take advantage of existing things. So there's a little gap shown in here between the pneumatic piston and the clevis, and that's where I decided to put things.
Okay.
So we knew we wanted to have a thing sticking from there that was moving up and down to measure what was moving in and out. Next up was finding a reading up on sensors. They're very exciting. I'm not saying that ironically, they actually are very interesting.
Many rabbit holes.
Yeah, I went on like a day-long rabbit hole on just inductive sensors, and we learned a lot. I think what we learned is also going to be useful takeaways for future sensor needs, because this is not the only sensor by far on our system. So we narrowed it down to an inductive sensor or a photo sensor, which ended up being a laser in this case. So
which
yeah, they both come in.
what? The leader?
What's good?
Did you say which ended up being the leader?
Well, we'll get there.
I misunderstood what you said, the last thing you said.
Yeah, there's a photo sensor, and there are various types of photo sensors. The one that we were really looking into was a laser sensor.
Okay.
Yeah. So they both come in industrial packaging, which gives us the right input and output that we needed. So that was kind of already there. Inductive sensors work by sensing a piece of metal that's nominally just steel that is in front of the sensor, the head of the sensor here. And they all come in different ranges. To get them more accurate, you'd want one that has a smaller sensing range than something that has like a really far range, but they generally are pretty small range. What's nice about them is that they're non-contact, they're fairly cheap, but they're typically used as non-contact limit switches, which actually we're using elsewhere in the robot. We're using inductive sensors as switches. So that means that it's either on or off, and this one can measure position. It does give you an analog output of what that position is, but it's not very accurate, and it's also not very linear, which is a problem for when we want to measure really small differences in that in the height of the piston. So that was kind of a bummer to learn pretty late in that rabbit hole that they're really not that repeatable. So I started looking at laser sensors, which kind of at first seemed cost prohibitive, but they really do fit the bill of everything we need. So they have the distance range, they're super repeatable, they have tiny resolution, not as tiny as like an inductive sensor, but you don't need it to necessarily be that good, and they're really linear. So the upside is it does exactly what we want and it's gonna work. The downside is it's kind of expensive. But I guess that goes back
Isn't
to
that everything though?
earlier
The
how
trip
you might
wanna
have to
take
spend
is
some
more
money now
expensive than the
to
trip you can take.
get what you need working, and then later, next iteration, change things up.
Okay.
So this is how the laser sensor fits into the system. We have this little diving board that is sandwiched in between the piston and the clevis that goes up and down with the motion of both of those. And the laser here is the red is its range. That is shown basically hitting the diving board and then reflecting off of it and going back to it, and that's how it measures how far away it is. And because it's linear, it'll give a certain signal, and that signal can be multiplied by the mechanical advantage between the diving board motion and the jaw motion, and then you have your jaw position. So yeah, this is when your jaw is all the way open. This is the position of the diving board. And then when it's all the way closed, it's not a huge change. That's why we needed it to be a pretty accurate sensor,
Sure.
but it is something that we can measure. So that's kind of next up is testing that on a bird to see if it gets us what we need.
Okay.
The end.
So you ordered this, it's coming tomorrow?
We
Yeah, so we
have
have
the
this.
sensor. It came in yesterday.
Okay, that's
So yeah, that's like the laser at the end.
oh yeah.
Well, yeah, we're getting the rest of the mounting parts tomorrow. Gonna try it out and see what we get.
Yeah, see what happens, see how now what are you going to be testing for here? Like what will make it successful for you when it's all said?
Yeah. I mean, in an ideal world, it would just plug in, there'd be a multiplier, and it would tell you exactly how far open or closed the jaw is. Some risks we have are there might be a lot of vibrations in the system, so the diving board might be going like this the whole time,
Mm-hmm.
or just like the whole thing is buzzing. That would then involve some signal smoothing, or maybe even just like a different approach, depending on how bad it is. So, yeah, I think we're hopeful that there won't be too steep of a learning curve, but you never know until you try it.
I got it. And in like the spirit of this whole 2 week test test of your expedience on solving a problem, did you embrace the engineering in public and make this include Andrew, include all your fellow engineers?
Yeah, absolutely. I think we had a lot of casual conversations and then one actual design review where um, it was kind of between those two sensors, and we talked through the pros and cons of them both and decided on this direction together because, yeah, it's many heads are better than one for
Absolutely.
sure.
Yeah. And you were leaning that way already, so it's almost a little validation, right? That your team felt the same way.
Um, I guess everyone deep down has what they think it should be, but I didn't try to push one way or the other because they're like I have my own biases and everyone else does as well. So try to be objective, although it can be hard.
Yeah.
I think we were hopeful that the inductive sensor would be a good solution, but once we started digging into the actual linear range on that plot, we realized that it was really coming really close to what our requirements were, and we were worried that we were going to spend all this time getting that in there and then realizing that it just wasn't going to be good enough by a small margin.
Yeah.
Uh, so because it was just right on that edge of maybe being a good solution, and because this is a prototype, it was like, let's just get the thing that is way more expensive, but we know it's going to work. And when you start to include the engineering times, the cost of the engineering time going into this, the cost of the sensor is pretty minimal, especially because we want the sensor so bad. It's just like, let's just guarantee it works
Yeah.
on the first time and go for the more expensive one.
Yeah.
We have something that will almost for sure work for now, and then as we develop the design of the whole thing, we can include provisions for a sensor that is cheaper or better in other ways in future iterations.
Sure.
It's not done.
Yeah, yeah. Like one of the suggestions that Joe emailed in was putting a rotary encoder on the pivot point. It was actually what you wanted to do in the first place before we even started this whole 2 week sprint
Yeah.
on this.
If we
And
could like change everything.
if we could change everything, and we're going to be going into a redesign on this whole lower assembly for the next system, and I think we'll probably be looking really close at that
Yeah.
because that has really impressive specs on it. Also non-contact, and from a cost perspective, it's also
Way
more
cheaper.
much more attractive.
Yeah.
Yeah, so on the next system, we'll probably be more thoughtful about including that
Yeah.
in the design earlier.
But for 3.1, you already have the established.
Yeah. We were working within the constraints of what we had and what we could just like slap on there. So I think this will work with what we have. Yeah.
Good. Good. I'm excited to hear what happens in 2 weeks if it's doing everything you wanted to do, and
We'll have to bring, you know, what would be great is we should bring Alex in here with a big smile on his face with some data showing what he's getting out of it.
It'll
Yeah.
either be a success story or a lesson in this is why you test your components.
Either way, there's something to be learned, right?
Yeah.
Yeah, you learn what you did right, or you learn how to fix what you did wrong. Not that wrong,
Yeah.
you know what I mean, though, but learn from it.
I'm sure there are always things to improve. So
Right.
we are.
Yep.
That's why 4.0 is on the horizon, right?
That's right.
Yeah.
That's right.
Yeah, this is now, but we're still like thinking future.
Yeah, you have to. I mean that's part of everything. It's thinking of outcomes, ahead of time so that you can help yourself down the line, right?
Absolutely.
Sure. Well, we are participating in, I mean, this is another collaborative thing. We're participating in this coolest things made in California contest. I'm gonna actually put that in the chat on LinkedIn because you guys are making this the coolest thing that is made in California. You're helping to solve a really big problem. Thinking differently about the way things have always been done. And it's innovators like you that are making a big, um, helping to heal the planet. There you go.
Yep.
We're slightly biased, but we think it's cool.
Yeah. Yeah. Yeah.
I do
It's
too.
pretty cool. Let's put some votes down. Yeah.
Yeah, there you go. So you can vote 5 times a day till tomorrow from multiple devices. So let's make it happen. And if you want to learn more about Urban Machine and what we do to help reclaim lumber for reuse, visit our website, urbanmachine.build.
Absolutely.
Guys, thank you so much. I'm looking forward to 2 weeks. See how it
Yep.
goes.
Thank you,
Thank
Cory.
you.
Bye, guys.